Welcome everyone, let's jump right into this math explainer where we're going to completely break down the entire real number system. I am so excited to guide you through this today. We're taking a journey, starting way back with ancient bones carved in the dirt, all the way up to those tricky, complex decimals and fractions you're absolutely going to see on your grade 9 exams. By the end of this lesson, you won't just be memorizing what a rational number is, you're going to understand exactly why it exists and how to completely master it.
Okay, quick look at our roadmap for today. We'll hit the dawn of numbers, the revolution of zero, rational numbers and decimals, the irrational breakthrough, the real number system, and finally we'll wrap up with exam prep and practice.
So, Section 1, the dawn of numbers. You know, numbers didn't just magically appear in a classroom, right? They started from a very basic human need to keep track of the physical world. Just take a look at this 35,000-year-old artifact, the Labombo bone. Imagine living thousands of years ago in an agricultural settlement along the Saraswati River. You've got a herd of cattle. How do you actually make sure none of them wander off during the day? Well, ancient humans solved this through a concept we call one-to-one correspondence. For every cow that left, they'd carve a tally mark, or maybe drop a pebble in a pot. When the cows came back, they just matched them up. This incredibly simple, practical act, that was the literal birth of the natural numbers, 1, 2, 3, 4, and so on.
And it's fascinating to see how counting evolved over millennia. We moved from those simple tally bones 35,000 years ago, over to the Ishango bone in the Congo, which remarkably actually grouped tallies into prime numbers. Fast forward to the Indian subcontinent during the Vedic period, and you have philosophers deeply pondering massive numbers, naming powers of 10 all the way up to a trillion. This intense cultural fascination with place values and powers of 10 perfectly set the stage for what is probably the single most important mathematical invention in human history.
Which brings us to Section 2, the revolution of zero.
So, we just saw how counting natural numbers helped ancient folks track physical objects. But here is the crazy part. For thousands of years, nothing simply wasn't considered a number that you could actually add or subtract. I mean, if you had 5 apples and gave 5 away, you just had a void. But in 629 CE, the mathematician Brahmagupta completely revolutionized math. He turned that philosophical void into an actual workable number, 0. And he didn't stop there. He expanded the number line backwards to create negative numbers, framing them as debts versus positive fortunes. Suddenly, subtracting a larger number from a smaller one made real-world economic sense. And just like that, we had the integers.
All right, Section 3, rational numbers and decimals.
Now that we've got whole numbers and negative integers under our belts, we have to deal with the spaces right in between them. As human society grew more complex, we desperately needed a way to measure parts of a whole, like dividing up land or following a recipe. Enter rational numbers. Look closely at this definition because I promise you this is going to be on your test. A rational number is any number that can be written as a fraction, p over q. The absolutely essential rule here is that both p and q must be integers, and q, the denominator, cannot be 0. Because let's be real, you can't divide a pizza into 0 slices. When we compare how these rational fractions look as decimals, we hit a really vital exam concept. Rational numbers will always do one of two things. They will either terminate, meaning they stop cleanly like 0.135, or they will be non-terminating but repeating. That means they loop a specific pattern forever, like 0.142857 repeating. Both of these types are strictly rational numbers. But how do we actually prove an infinite repeating decimal is a fraction? Let's break this calculation down together, step by step. Take the decimal 0.1666 going on forever. Step 1, we set it as x. Step 2, we multiply by 10 to shift the decimal point just past the non-repeating part, which gives us 10x equals 1.666 repeating. Step 3, we multiply by 10 again to shift past one full repeating cycle, giving us 100x equals 16.666 repeating. Now here's where the magic happens. When we subtract the 10x equation from the 100x equation, those infinite trailing sixes completely cancel each other out. We're left with a clean 90x equals 15. Divide by 90, simplify that down, and boom, we've mathematically proven that 0.1666 repeating is exactly the fraction 1 over 6. Okay, time for a little interactive practice. I want you to pause this explainer right now, grab some paper, and try to convert this mixed repeating decimal, 2.357, where only the 7 is repeating, into a p over q fraction yourself. Just use the exact steps we just learned. Go ahead, hit pause now.
Welcome back. Let's check your work. First, you needed to multiply by 100 to get that non-repeating 35 out of the way, making 100x equal to 235.7 repeating. Then, multiply by 10 again to shift past the repeating 7. Subtracting them gives you 900x equals 222. Now, a super common exam mistake here is misaligning the decimal point before subtracting. You always want to ensure you isolate that infinite repeating tail perfectly so it cancels out to 0. Your final answer should simplify to 1061 over 450. Great job if you got that.
Real quick, before we leave fractions behind, I want to share a massive exam tip that is just a truly beautiful mathematical shortcut. Look at the fraction 1 over 7. Its repeating decimal is 0.142857. This is what we call a cyclic number. If your test asks you to find 2/7 or 3/7, do not waste your time doing long division. Multiplying this decimal just shifts those exact same digits in a continuous circle. So 2/7 is just 0.285714. It literally just loops. How cool is that?
Moving on to Section 4, the irrational breakthrough. So we just proved that fractions can create endlessly repeating decimals. But did you know ancient geometric construction actually caused a profound crisis in the mathematical world? For centuries, mathematicians just assumed every single length in the universe could be represented as a neat rational fraction. But when ancient scholars in India, like Bodhayana, were constructing complex geometric fire altars, or when the Greeks were studying right triangles, they hit a massive wall. They discovered lengths like the diagonal of a square that completely defied fractions. They resulted in decimals that went on forever, but never, ever repeated a pattern. They had stumbled upon irrational numbers. This brings us to a classic proof showing exactly why one of these numbers, the square root of 2, completely shatters the rules of fractions. It uses a method called proof by contradiction, and heads up, it is a very famous exam question.
Now don't let this proof intimidate you. It's like a giant puzzle. Let's walk through the logic. Step 1, we pretend the square root of 2 times is rational. We say it equals a fraction p over q in its absolute lowest, simplest terms, no common factors at all. Then we square both sides and rearrange the algebra. Step 3 shows us that p squared equals 2 times q squared. Because it's a multiple of 2, p absolutely must be an even number. If we substitute that back in, step 4 reveals that q must also be an even number. And boom, step 5 is our logical contradiction. If both p and q are even, they share a factor of 2. But remember, we started by stating they were in lowest terms with no common factors. Therefore, our initial assumption was completely wrong. The square root of 2 cannot be written as a fraction. It is officially irrational.
Section 5, the real number system.
Okay, we've tackled natural counting, negative debts, rational fractions, and irrational diagonals. Now we finally have all the puzzle pieces required to build the complete universe of continuous numbers. Think of this diagram like a set of nesting boxes. We start with the natural counting numbers, tucked inside the integers, which include our zeros and negative debts. All of those sit safely inside the rational numbers, our fractions. And living right next door, completely separate but equally important, are the irrational numbers, like the square root of 2 and pi. By combining the rational and the irrational together, we form the completely unbroken real number line. Every physical measurement, length, or temperature in the known universe has a spot right somewhere on this continuous line.
Finally, Section 6, exam prep and practice. Let's lock this in.
Here is your ultimate concept cheat sheet. I highly recommend taking a screenshot of this list right now so you can memorize how these different number families stack together to form our mathematical world. Keep a close eye on the strict difference between repeating decimals, which are rational, and non-repeating decimals, which are irrational. That always trips people up.
And for those of you aiming for top marks, here is an advanced, high-level exam challenge to truly test your algebraic mastery of rational numbers. Write this equation down and give it a try after this explainer finishes. A little hint: proving this requires you to remember your polynomial identities, specifically squaring the sum of x, y, and z. It's a fantastic brain workout.
For my visual learners out there, here's some final geometric practice. Try calculating the hypotenuses of this beautiful square root spiral using your ruler, your compass, and the Pythagorean theorem. It is just a brilliant way to visually map out those irrational lengths we talked about, growing step by step from root 2 to root 3 to root 4 and beyond.
You guys have done amazing work today.
You've conquered fractions, decimals, truths, and you've truly mastered the real numbers. But I want to leave you with one final provocative thought. What actually happens if we step completely off that continuous real number line? What if I told you there's a whole separate dimension of mathematics called imaginary numbers, numbers based on the square root of a -1, and that these quote-unquote made-up numbers are exactly what powers the microchips in the mobile phone you might be holding right now? Mind-blowing, right? But that journey is for another explainer. For now, keep practicing those rational fractions and keep that mathematical curiosity alive.